Thank you all so much for joining us today for Climate Change and the Future of Sustainable Farming, presented by renowned climate scientist, Dr. Brenda Ekwurzel from the Union of Concerned Scientists. Dr. Ekwurzel presents frequently to a range of audiences on climate science, educating the public on practical, achievable solutions for climate change. Prior to joining the UCS, Dr. Ekwurzel was on the faculty of the University of Arizona in their Department of Hydrology and Water Resources with a joint appointment in geosciences. She has studied climate variability in places as disparate as the Arctic, where her research brought her to the North Pole. Dr. Ekwurzel earned a BS in geology from Smith College and an MS in geoscience from Rutgers University. She holds a Ph.D. in isotope geochemistry from the Department of Earth and Environmental Sciences at Columbia University's Lamont-Doherty Earth Observatory and conducted post-doctoral research at Lawrence Livermore National Laboratory in California. A widely quoted expert on climate change, Dr. Ekwurzel has appeared on ABC News, CBS News, Good Morning America, CNN, the Fox News Channel, NPR, and the Colbert Report, and has been cited by the Washington Post, USA Today, Associated Press, and Reuters. We are very fortunate to have her with us today. So with that, Dr. Ekwurzel, thank you again for being here, and I will hand it over to you.
Hi, everyone. It's so good to see you virtually, and thank you for joining us this evening. I wanted to share my screen with you first, so let me do that. And I just wanted to thank everyone at the basically New York Wine and Grape Foundation for inviting me for this opportunity, and to Suzanne Hunt for connecting me with your wonderful organization. And so I'm going to take a tour of climate science that may be relevant to wine growers in the New York region and the Northeast in general. And also, I really look forward to your questions, because I think that's where perhaps we can have a very interesting dialogue. So I'll give you a taste of some of the ideas I thought I'd lift up. Some of this may be review for some of you, and others, it might be a fun exploration of new topics. So with that, I will go forward. Let's see. So first, I want to talk about the climate change of today, what has already happened. And I'll give you a headline. I just recently blogged about this, so I'll use the framing that I used so we have just finished the hottest decade on record since record keeping for the global average surface temperature has happened. And I really was struck by looking at the curve from the federal government, especially the NOAA, National Oceanic and Atmospheric Administration, decadal curve. It really has become as iconic as the famous carbon dioxide increase curve known as the Keeling curve. So here it is. At the bottom right is the Keeling curve, which is the increase in atmospheric carbon dioxide. And above that, with these bar charts, are showing from the 1881 to 1890 decade is the first bar, below the zero line, which is the 20th century average global surface temperature. And you can see that with each decade, certainly since the mid-century, in the 1950s decade, we have seen an increase, and the amount of increase certainly seems to be increasing with a greater amount. And so it's getting hotter. But that's a global average. I mean, what would that really mean for New York State and the regions where wine growing and grape growing is going on? So let's take a look at the global average to get a taste of what would it be like in New York. So here is the map of the 2020 year, the average over the year, but shown in this map form. And you can see the change compared to the 1951 to 1980 average global surface temperature. So what you see is that most of the warming is happening in the higher regions, It's more happening over the land areas compared to the ocean, and especially in the high northern latitudes of the Arctic and Eurasia. So let's see, but this is the global average. And let's look at just last February. What was the monthly average? Let's look at the same map from NASA, but just look at February. And what you see is a very different picture in February. So if you're interested in ice wine or worrying about the freezing temperatures or anything, then looking at the climate and how it's changed in relation to the month of February, you would be looking at the monthly maps. And what you see is this huge swath of cold in North America stemming from Alaska all the way down to Texas. And you may have heard about the polar vortex affecting the electricity grid system in Texas and led to a massive disaster. This winter, we did have a lot of changes happening in the Arctic that created a lot of cold for big parts of North America, as well as you can see in Northern Europe, in the northern Russia, Scandinavian sector, Finland and Western Russia, northern. But if you look at, there were heat records being broken in Southern Europe and Spain and France, and certainly parts of the Himalayan region between India and southern region of the Eurasia. So what you see is that Greenland was really hot, Alaska was really cold, Texas was cold, and parts of Nova Scotia were warmer than average. So what is going on here? You may have heard this term, the polar vortex, and I'm going to share with you a quick 2-minute video. And this was from February 1st. And this is a meteorologist from New York City. He is talking about the climate connections, and this is a screenshot from it. And so what I want to do is, before we go into that clip, I just want to review a couple terms that he's going to mention. And so Jeff Baradelli is going to be talking about some of these terms. It's a 2-minute clip, and I think it's a much better dynamic illustration of how what's happening in the Arctic could be affecting, and the Pacific could be affecting weather in the New York region. So here we go. Here are the terms. Look at the left panel. Basically, the Arctic polar vortex is a strong band of winds in the stratosphere, and it surrounds the North Pole, and it's really high up. It's really in the stratosphere. It's about 10 to 30 miles above the surface of the Arctic. And what you see on the left globe is it's a tight band. It's a stable polar vortex typically, and it doesn't typically interact with the polar jet stream, which often brings weather to North America and the northern hemisphere. And the reason it's called the jet stream, it's within the troposphere, and it's at the level with that jets are flying. So it tends to have this strong west to east flow in the wintertime, and that's a typical situation, although since the 2000s, we've started to see more and more episodes of what are called the disrupted polar vortex. And what you're going to see in the video is courtesy of CBS News, their visualization of what happened when we had a major disruption of the polar vortex and what that meant. So look at the right globe now. So the polar vortex is disrupted. It tends to be pushed off of the polar region. You'll see why in that video a little better. And the cold air pushes down into the northern hemisphere. It interacts with the polar jet stream, and the polar jet stream takes a longer path around the northern hemisphere. It becomes much wavier, and you'll see that you'll have what we kind of call it, it's like opening the refrigerator door of the Arctic. The cold blast comes down and it can hit southern states within the United States, and yet other warm air from the lower latitudes gets far up north. And depending on the pattern it sets up, anywhere in the northern hemisphere this can happen. And we're starting to notice certain patterns of where it happens more often than not. And once it sets up for the winter season, sometimes we can have, by the time this one happened, it was about the third disruption of the polar vortex, but it was a pretty bad one. especially the one that happened after this was in the Texas situation with the disruption of power supply within Texas. So let's go to the video clip. I'm going to see if this works, and we'll see if you can hear it. Okay, here we go.
Great. So do you want to talk about that? Because we have a graphic to show on this sudden stratospheric warming. It's a really amazing phenomenon. Okay, all right. I'm glad you gave me the green light. That's all I needed to hear. So here's what happens. It's pretty amazing. It's a natural occurrence, but about 2 to 3 weeks ago across the Arctic, it warmed up 100 degrees in a few days, about 50 to 100,000 feet above the North Pole. When that happens, it causes an imbalance, a disruption.
It seems that folks can hear the clip, but they can't see it.
Oh, they can't see it?
Arctic
okay, hold on 1 second. Let me stop sharing and then share the screen. Maybe it's because of, hold on 1 second. Let me share it. Okay, let's share that. Do you see it now?
Yes.
Okay, so we're at this point where it warmed 100 degrees, about from negative 92 degrees up to 8 degrees, which for the Arctic is a sudden warming. It's a massive amount of warming. And so if you heard that part, here's the start of what's going on, and you'll see most of the graphics. Okay.
To warm it 3 times the pace of the rest of the globe. So because of that, everything is discombobulated. It throws the steering currents off kilter. And when you do that, you get a very convoluted, wavy jet stream with all kinds of blocking, like a traffic jam in the atmosphere. So storms get stuck. So what happened? Well, in California, this same storm a couple of days ago got stuck over California for 2 to 3 days, produced 15 inches of rain, over 100 inches of snow. Then all of a sudden, the storm takes off and flies across the country, only to stop short again right here in New York City and get stuck in another blocking scenario, courtesy of a sudden stratospheric warming and climate change causing the storm to stop. It's kind of a combination of both. Then add to that the atmospheric river in California and this conveyor belt of moisture from the Atlantic. You know, it's a warmer atmosphere. A warmer atmosphere is like a bigger sponge. It holds more moisture and it wrings out more of that moisture in the form of heavier snow and rain. So 6 of the top 10 snowfalls in New York City have all occurred since 2000, despite a warming climate. That's because it's just cold enough to snow, but there's more moisture in the atmosphere for blockbuster snowstorms. Was that too nerdy and geeky for you?
No, and that actually helps me to understand, a lot more. Often when
Okay, I'm going to stop this share again because clearly to get back to the PowerPoint. Okay, so let's look at this one. And we can review this again, but the idea is where this sets up for a season can be very disruptive for extreme events, especially in the wintertime. And the latest science is showing that not only El Nino and La Nina in the Pacific, which determines dry and wet patterns of weather for a season in North America and all around the world, this change in the Arctic region is interacting with that, the El Nino or La Nina or neutral conditions in the Pacific, and we have weather patterns that are moving across. The bottom line is climate change is changing weather, changing the patterns, and it's changing the severity of these events. So that was what happened in February. And what we saw was that the February anomaly was looking very different from the global anomaly. So that's one thing about climate changes. It's a lot about averages, but sometimes these averages of what happened in North America the year before, and then we'll see how it looks in 2021, month by month, we can have very extreme weather events within this average of warming. So that's one of the, especially if you're growing crops that depend on understanding how many freeze days there are, how cold it gets, how warm it gets, what the extremes are. It's really important to pay attention to the type of research and science that is predicting some of these Arctic blasts weeks in advance so that you can prepare. So this is back to the National Climate Assessment. And I said, we're going to talk about what has changed with climate change. With all these extreme events happening, when you average it out, what you see is that the extreme event in the form of precipitation is for in any given year in New York State, what was the heaviest rain event or the heaviest snow event? And we log that in this graph and say the heaviest 1% events, how much volume of water is falling in that heaviest rain event. So if you look at the 20th century average plus the first decade or so until 2016 and see what that changes in the New York State region, it averages about, around 38% more water is falling in the total annual precipitation of the heaviest rain event. If you look at all the events, if you look at just the 1958 to 2016 period, that shows you what this accelerating climate change is doing, because the amount of rain, if you were planting your vines in the 1950s and keeping your vineyard going, and then you were looking at those earlier records, in the heaviest rain event that might cause soil erosion, might be disrupting different soil situations, maybe even causing damage to your infrastructure. 55% more rain on average is falling today than it did in the late 1950s. So if we take this going forward, took this old postcard of a very old vine, what is the lifetime of planting some vines that you want to grow for 2 decades, 2.5 decades, maybe even 3 decades? What would be the climate towards the end of that lifetime of that particular vine planting? Thinking about that far out is kind of where the climate change toolkit and the National Climate Assessment and the US Global Change Research Program are great resources to consult with their toolkits to look at your particular area. So here's just an aggregate for the whole continuous continental United States. And we see that, let's look at the lower scenario, because the world has agreed that we're gonna try to stay within the Paris Agreement. And that would be closer to the lower scenario. In the New York State region, you see that it's anywhere between, from today's level of already increased heavy precipitation compared to the 1950s, late 1950s, that you could see anywhere between an extra 20–30%, and in some parts of New York State, 40% heavier, more volume of rain falling in your heaviest precipitation event, which could be a rain or a snow event. So it's becoming more intense. And so you have to have climate resilient agriculture. The other obvious change with climate change is the lengthening of the freeze-free period. So the growing period is getting greater in the New York State and the Northeast of the United States. So by the middle of the century, the freeze-free period across most of the Northeast is expected to lengthen by around 2 weeks under that lower emission scenario, sort of just above what the Paris Agreement target is, but where we are currently heading. So that's in around the 2040 to 2069 year as a planning horizon, plan for 2 extra weeks of growing. The other aspect is taking all of this into account, how can we have climate resilient wine growers? And the reason I showed the soil in this slide is because with regenerative agriculture and some of the policies that are coming down the pike that we expect, that there probably are going to be resources within the United States and many parts of the world to encourage agricultural sector sequestration of carbon for longer periods than perhaps has been the case in the past. So even if there are practices that may seem a bit costly now to do in order to get that extra carbon storage in your soils, which helps with all sorts of many other benefits to wine growing and other agricultural practices, it will likely pay if policies are passed to really encourage this type of sequestration, because it helps shave off and slow the pace of warming. So I'm going to share, my colleague Marcia DeLong is a senior scientist in the Food and Environment Program at UCS. And this latest blog I'm going to show the 6th way. She outlines a lot of ways that Agricultural Resilience Act is an act that is before Congress, is really there to help farmers fight climate change. And here are in the 6th principle, here are what Marcia is proposing. So what the top line is that US agriculture contributes about 9% of the nation's heat trapping emissions. So the goal is to get to 0 emissions by 2040. And the other goal is to restore at least half of the lost soil carbon. So we've lost a lot of soil carbon in the United States based on past practices. And one of the ways to achieve this is, in addition just to the many co-benefits, is to maintaining year-round cover, which many of you likely know, this is review, of at least 75% of the cropland areas, or areas in between the vines, and which is already gaining momentum, and practices and best practices are being shared among all of you, I imagine already, and through the foundation. So increasing the soil carbon storage, incentives for that, which also, as I mentioned, the intense precipitation is one of the signatures of the New York State region. It's one of the largest in the United States. It's a very intense precipitation zone. It's gotten worse since the 1950s, and it's going to be even worse going forward, depending on how warm we get. So some of that warming's baked in. Expect more intense precipitation. So when you are storing soil carbon through crop cover and other techniques, one of the co-benefits is that you don't lose as much of your soil during some of these really intense precipitation events. One of the proposals is to eliminate farmland and grassland conversion, which is an obvious loss of carbon. And there's a big effort in that particular act to reduce food waste, because people calculate that maybe 40% of the food in the US is currently wasted, which ends up in landfills, as well as also loss of heat trapping emissions to the atmosphere. So this is just talking about the carbon. We also know that nitrous oxide is a greenhouse gas, and methane is part of this carbon, and trying to keep the soil carbon. You have anaerobic conditions, aerobic conditions, and depending on the form that it's released, if it's released as methane, it's more harming for the temperature increase than if it's released as carbon dioxide. So that's something to keep an eye on as well. So my goal was to give you a flavor of some of the basic top line changes with climate change. There's a lot more detail we can dig into with discussion and question and answer period. So I want to just tee this up and give you a flavor so that we get to your questions, which I'm most interested in. Thank you so much. I really appreciate it.
Thank you, Brenda. We have a few questions that came in.
Okay.
The first one is, what do you say to those who argue that the Earth is undergoing normal heating and cooling cycles that have always happened over the course of its existence? I always find this particular pushback to be frustrating.
Sure. Yeah. That is, well, number one, we have the science of record keeping, including in, there was a lot of viticultural records. There's records of ice breakup. People used to bet on them, some of these ice flows breaking up in a river. Some communities have had that for a long time period. There's lots of records, agricultural records, planting dates and so on that people have analyzed. So through human history, we know that we have finished the hottest decade. And we also, through paleoclimate, we know that the Earth temperature has changed in the past. It's been warmer, there's been more carbon dioxide, and we also understand the natural causes of those, which happen to do more with the position of the sun and the Earth and the elliptical orbits. So planetary motion that happens on thousands of years, or the pace of the ice ages, and even further back in time. And what we always see in history that's archived in climate archives, the ice cores, lake cores, lake varves, pollen records, all sorts of records on Earth. We know that whenever atmospheric carbon dioxide increases and methane and other greenhouse gases, especially those couple, that there's natural warming, but when you release the carbon into the atmosphere, it really accelerates the warming. And in Earth's past history, sometimes that warming happened because of spreading plates, and it was millions of years of release. And then other times it was thousands over millennia. And now we're releasing over just a century, much higher amounts that have ever been released in the past that fast. So the faster it was released in the past, we lost lots of extinction events, we get loss of life. But when it was released very slowly, life did survive better. There were some extinctions, but pretty much there was species and systems were able to adapt and move. The pace that we're doing now is so fast that many species and extinction events are expected. So if we were to do a very high emissions scenario, even with Paris Agreement, we are likely to lose most of the tropical coral reefs and likely the summer sea ice in the Arctic.
That's incredible. Our next question comes from the Finger Lakes. Last summer in the Finger Lakes, we were short of rainfall, with the benefit that there was less farm runoff into the lakes. But the map shows greater rainfall. Should we expect increasingly erratic patterns, or rather no predictable pattern of hot and cold, dry and wet?
Yes, that's a really good thing. I remember before the Arctic became a bigger player, the warming trend since the 50s, you started to see in the Great Lakes region, trade used to be very disrupted in the winter ice cover and the ship movements and stuff like that. It was Great Lakes ice cover was a big deal. And you started to see less and less ice. And that would sometimes release moisture into the atmosphere. And if there was a cold blast, you have those lake effect snows, famous lake effect snows in the Finger Lakes region, as well as anywhere downwind of these Great Lakes. And so there was the thought that in some